last time we see streaming algorithm, which is like a sublinear space algorithm. Like it's quite modern, like 20 years ago. Today, sublinear time algorithm that I will present today is just actually like 6 years old. It's really new, and the presentation today actually is just shown like it's shown by the author like this year. It's like a simplified version, which I like a lot. And you see, the problem that we look at, like how to get sublinear algorithm, is the vertex coloring. So here you have a graph, right? And let's say that like you have a bound on the maximum degree of a graph. Like here, the maximum degree is 3. And we will look at k-coloring of a graph. What is k-coloring? It's just like assignment to, it just assigns colors to vertices, right? Such that each vertex is colored by a number from 1 up to k. So here is like a 3 coloring of this graph because there are just 3 colors. And what we need from this is that for any adjacent vertices, they must have different colors, which is like this in this graph. And okay, it has some like you can use vertex coloring to color map so that you can there's no adjacent countries that have the same color, except that actually it's not true here. So here too. Okay, anyway. But in general, like why do we care about vertex coloring? So the point is that like for each color, right? Each color kind of have vertex set of each color have no connection to each other. And you can think of, sometimes you can think of each edge as some conflict between two nodes. And when you have like some coloring of a graph, then you can basically cluster. It means that you can cluster vertices into sets such that each set, there's no conflict between each other. So that's like, it's useful in high level like that, but actually it's used a lot in many, like as a subroutine on many other problems. Okay. One comment about coloring is that, okay, I'm not sure you have seen this, but like just checking if a graph has the 3 coloring, this is a hard problem. It's NP hard. You can reduce it from 3 set, for example. But how about like if I ask this, if I ask you, can you find me, like I promise that the max degree is at most delta. Can you find me delta plus 1 coloring? Any ideas on like why this might be easy? Blake, yeah, go ahead.
Do you just change one of the colors to a different color? Like just add a different, is it delta? If delta's 3, it's like 4 colors. Just change any, you pick any of them, make it a new color? Or no? Is that not the question?
That's not the question. What I mean is that when I give you any graph with maximum degree delta, is that like, how can you color vertices so that no adjacent vertices have the same color in polynomial time?
Yeah. I think you could just start with like the maximum degree nodes, and because if you have a delta plus 1, if it has 3 neighbors, you can color each neighbor a different color than the one with the maximum degree node. I feel like you could almost like write a recursive algorithm to kind of then recurse on.
That's the idea. Like, I mean, you see like actually the simpler way to do this, but the idea is that you have delta many neighbors at most. So even if your neighbor have all different colors, like they consume all different colors, you still have like a 1 more color to pick. So that is a valid coloring. So that's the idea. And just from this, it just gives you a linear time algorithm already. How? Maybe just fix some arbitrary ordering of vertices. Fixed order. And then like just loop on like from I up to n. Then for vertex vi, just pick a color that is not used by the neighbor. And you know that it must exist just because like vi has degree like if this is vi, it might have degree something. The degree is like degree of vi. But even if all of these guys have different color, let's say 2, 3, 4, up, like all these guys, the number of this node is still at most delta. So even if they all have different colors, you can still pick one color. That is like it's not used by any of the neighbor. So just do that, right? And then color vi with C. And you can see that the total running time is just like we just spend time like on each node. We spend degree time, so that's linear. In other words, you can say that like on each node you spend at most delta time. Okay, so that's a simple algorithm. Right. But yeah, today we will see like that you can do better. Not like linear is not enough. Sometimes you can do better. So what we'll see is that you're gonna find delta plus 1 coloring in expected time. It's a randomized algorithm, so you have expected time of n squared over delta with some log. So it means what? It means that like if let's say you have a really dense graph with delta like n, like in dense graph you can have n square edges, right? But when delta is close to n, then this is actually run in linear time, like basically linear time, like basically close to n instead of n square.
Wait, wouldn't it be n log n?
Oh, n log n, yeah, n log n, right? So when delta is close to n, this is n log n, yeah, which is sublinear in the size of the graph. Like the graph, when m is let's say like n, so delta is like order of n, then this is just n log n, which is like much smaller than the number of edges in the graph. So it means that you don't need to read the whole graph even. But I will need to assume one thing though, that is I assume that at least I can, like the adjacency matrix of the graph is given to me. And I need to assume this, I need to assume some representation of the input, because right now I do something without even reading the input, right? So if I don't promise any representation of the input, I need to spend linear time to read the input, so that you cannot hope for sublinear time. But like assuming adjacency matrix is something that like are really weak, and you can assume this many times. Yeah, and this is discovered like just 6 years ago. Yeah, and we see what it is today. And by the way, like if you combine with the previous algorithm, that previous simple greedy algorithm that run in n delta time, then take the mean, like take the best of both algorithm, you then get like an algorithm that takes at most n root root of n log n, yeah. Which is, it means that like it's sublinear in dense graph, like a sublinear in the number of edges for dense graph. Okay, so let's see how to do this. The algorithm is going to be super simple. So we're going to fix some ordering again of vertices and loop over our vi from 1 up to n. And what we're going to do is like we're going to sample a color. We choose a color randomly. And then for each vertex that has color C, we check if Vi and C are adjacent to each other. So you kind of maintain whenever you color some nodes, you maintain that set like you have a set of vertices of each color. You maintain that. So now you just check for each vertex with color C, check if Vi is adjacent to C, to that node U. So what you do here is you spend this time. It takes time proportion to the number of C color vertices, right? So not the number of your neighbor, just proportion to this. And if none of the vertices with color C is adjacent to Vi, it means that you can color Vi with C. Else you just repeat. You go to step 1 and resample. Just try again and again until you succeed. That's the algorithm. Any question about the description? Good, right? Okay. So you see that at the end, once you terminate, you get a delta plus 1 coloring. Just because before we color Vi, we make sure that Vi is not adjacent to any node with the same color. And we choose a color from this set. So you get a valid coloring. So now the only question we need to ask is how fast this algorithm is. Okay, so let's try to analyze this. Okay. So I will gonna denote our xv to be the number of queries or number of adjacency, number of times that I queried adjacency matrix when I try to color the node V. Just the time that we spend on the node V before we can color V. So it means that the runtime of the whole algorithm is just a sum of xv. Okay. And now we note that xv is a random variables, right? It's not it's not fixed, and we want to compute the expected running time, which is going to be then by linearity of expectation. It's just going to be a sum of expectation of xv. So we just need to analyze expectation of xv, how much time we spend on each node in expectation. And my claim is this. Okay. The claim is that the expected time that we spend on V is going to be something like n over delta plus 1 minus this thing. Let's call it degree before V. What I mean by here, I mean it just degree before V means it kind of count the neighbor of V that is ordered before V. Okay, so for example, if I have v1, v2, vi plus 1, maybe the name like maybe the degree of vi is right now like a 7, but here degree before vi is 3. Okay, like this is the ordering with respect to pi. So this is basically something that kind of range from like degree before could be 0, so it kind of range from this thing up to n. Okay. So it's between the n over delta and n, and but if degree before is is big, it's close to delta, it's really basically delta, then this is n. Otherwise, if degree before is kind of even let's say this is, if this thing is less than 0.9 delta, then this would be like a order of delta, n over delta. If degree before v, then it's going to be order of n over delta. Okay. So this is just so that you get some feeling about this. Yeah.
Why is 0.9 delta the cutoff?
Not like anything that is just constant factor less than delta. Then what is below here is just gonna be omega of delta, and this would be order of n over delta. Yeah. So 0.9 is arbitrary. Yeah. All right. Okay. So right now it's not clear why this is the case, but we will need to analyze this, and it's unclear. Okay. But let's see why. So we want to prove this thing, right? And to do this, we're gonna look at we need some concept. So I'm gonna say that a color C is useful for a node V if no neighbor of C is color C so far. That is, if I sample a color C, then I can color this node with C. Otherwise, if some neighbor already used this color, then it's not useful. Okay, and VC is just like a set of vertex set that is color C. Okay, now if C is useful, okay, I want to analyze this. I claim that like if C is useful, and let's say that I am given that C is sampled as a first vertex, as a first color, then how much time I would spend on V? The time that I would spend on V is just like the size of vertex set with color C. I just like query all of the node with color C, and I check that okay, I'm good, that there is no one adjacent to me, and I would color V with C. I'm done. Okay. So okay, what if C is not useful? Can you tell me what would be this thing? So I claim that it's gonna be x of V, the time that we spend on x on V, given that C is sample first. Well, it's gonna be, first of all, we're gonna spend time VC. We're gonna query all node with color C, and then we're gonna see that okay, V is adjacent to some of this guy. And then what should be this? Like we need to spend more time now. This is some simple expression we can put here. What should this be? Any random idea? Basically, once we check all of the node with color C, we see that okay, some of them is adjacent to me, and now I basically need to start over, right? As if I know nothing. So yeah.
I mean, I don't know the exact notation, but you're just gonna kind of repeat the process on the other colors.
Yeah, we're gonna speed the process, and basically when we speed, just repeat the whole process. Then I can just write this thing. Right, this is like the time that I would spend on V in expectation if I know nothing. This is the time that I would spend on V if I know that the first color that I sample is not useful. If I know that the first color that I sample is not useful, I know that I need to spend this much time, and I start over. So this is just the thing that you're gonna spend. Yeah.
But don't you know a little bit more information than just E of XV? Because like E of XV assumes you don't know anything, but now you know that you've ruled out one color.
Right.
So isn't this like? So I mean, I guess it's.
We know we as a person know, but the way that the algorithm works, it just resample from any any set of it just resample a random color again, without regarding what happened in the past. Right? You see. When it's not useful, we're gonna see that okay, we go to else case, and we do step 1. In this step 1, we don't exploit the knowledge that we know something before. Just redo here. Yeah.
So for step 1, it's like completely random what color we're checking. Like we're not keeping track of what color we're checking. Okay.
No. Yeah. We could keep track, but just for a simplification, just to make analysis nice, you don't do that. Okay. So you agree with this, right? Okay. Okay, so this is a non-trivial step. Okay. But now we know all the case, when C is useful and when C is not useful, what will happen if C is sampled first. And now what we can do is just try to compute expectation of XV. Okay. And let's see if it's better to. Yeah, I'm gonna try to write on the board. I'm not sure it's better, but yeah. So expectation of XV, right? Okay. Everyone see this, right?
Yeah.
Okay. So I'm gonna just start condition on the probability that C is sample first and then expectation of xv, given that C is sample first. Sample first. Okay. This is just by law of conditional expectation, right? And now, what do you have? What is this?
1 over delta plus 1.
Yeah, this is 1 over delta plus 1, right? Okay. And this we have 2 cases, right? So let's maybe let's try to write it in 2 cases when C is useful. Then this is gonna be this thing times CV, then plus C not useful, full, then 1 over delta plus 1, just from here, and this thing. Yeah.
This might be a dumb question, but on the board, it says that the expectations are bound by VC and the expectation.
Oh, good.
Okay,
Yeah.
okay.
Yeah, good. All right. So now I can just say that, okay, this is for all C, it's like a VC, and not useful, 1 over delta expectation.
Yep.
What is this? Like this is sum over all vertices. Well, like the sum of VC is at most n. So this is at most. Okay. And then here we're gonna need to bound the number of not useful vertices, not useful color. But the number of not useful color I claim is just gonna be at most degree before. XV over delta. Because like if this is a V, and then if you look at all of the neighbor before V, then like in the worst case, maybe in the worst case, this is the case when all of the neighbor before V have distinct colors. So that's the total, that bounds the number of not useful color for V. Right. So this is sum over all these many terms at most. Okay, now you kind of basically you are done just by kind of move this term here and rearrange. Like you're gonna get from here you get that this is what delta plus 1 minus over this thing. I just move this to minus this, and this is at most. And then I move this, like I cancel this one. I move this to divide this thing. So we get the claim. All right. Okay. So that's like the part that is not trivial. Okay. So now, given this thing, now basically we kind of like, okay, given that we have analyzed what is expectation of xv, the time that we spend on xv, we now know the expected runtime is just a sum of this guy, which is like this. Yeah.
Can I ask a question about the proof? On the first line to the second line, are you basically assuming that in the worst case the probability that C is useful is 1, and the worst case the probability that C is not useful is 1? Because like C is either useful or not useful, but we don't know. Are we just saying we don't know the probability of either one, and so we say both are in the worst case, or am I misinterpreting that stuff?
Not really. Yeah. So it's what you interpret is not quite correct. So each at any point of time, each color is either useful or not useful for a node V. Okay. And we just look at that time and we just partition that set of color into two sets.
Okay.
Useful one and not useful one.
Okay.
If it's useful, we're gonna spend this time. If not useful, we're gonna spend this time. And C is sample like for each node. For each color, C is sample with this probability.
Oh, okay, got it.
Yeah. Okay, good. All right. So now back to this, we have like a expression of our running time. Okay. It's not too easy to analyze this still, but you're gonna see that we can analyze it. Like just for some intuition about this, right? Again, if the degree before V is not too big, let's say it's not too big for most vertices, then what you're gonna get? You're gonna get that like this sum here. It's gonna be like each term is gonna look like 1 over delta. If this is the case for let's say all vertices even. Okay. Then each of these term is like 1 over delta, and you sum over all nodes. So it's like an n squared over delta, which is like what we kind of want. But can we hope for this? Can we hope for this thing? If our pi, our ordering would satisfy this one, then we are good. But actually, it's not always the case that every ordering would satisfy this. Okay. So let's look at some example. Let's say that the graph is the data regular bipartite graph, which is just a graph where every node has the same degree, delta. You can think of complete bipartite graph, for example. Can you tell me, like, for this graph, can you tell me what is an ordering that is actually bad, in the sense that it will not satisfy this one? There is like a one ordering of vertices such that for many vertices, actually like the degree before is basically just delta.
Why doesn't one of the nodes only have degree 2? They don't all have the same degree, do they?
Oh, okay. You have this. Yeah. I missed this. Yeah. It's a bipartite graph where everyone has. Okay, I missed many edges actually. This thing too. Okay, now it should be everything. Yeah. Yeah. Can you order vertices such that many of like nodes after ordering the degree before is still delta?
is that you go all along the left side and then all along the right side?
Exactly. Thanks, John. Yeah. You can just order vertices in any way such that every guy on the left side is before every guy on the right side. Which means that if you look at like the degree before of the right guy, well, like all of its neighbors are before it. Are before this guy, are before this right guy. So the right degree of this, the before degree of this one is just delta. And this one is delta too, this one too.
Wouldn't that kind of even out with the fact that the ones on the left side don't have any previous neighbors? So like the ones on the right are really bad, but the ones on the left are really good.
Yeah, like it's true that like all of this one, the degree before is 0. However, if you look at like how this thing looks like, so it means that like a half of the nodes, you're gonna spend basically n for the right vertices, and for half of the node, you're gonna spend this for the left guy. This is the time that you would spend on on the right, and this is the time that you spend on the left. But when you average these two, basically it's just this right. So yeah. So the total time is still of order n square. When you sum up this thing. Okay, so we say that at least for some ordering, like this expression is big. So this is like a sum ordering is bad, at least for our analysis. It's not clear that this is really bad for the algorithm. Actually, I asked the author, Seper Asadi, he believes that actually any ordering is fine, but at least for this analysis, it's not good. Like there's some for this analysis, some ordering is bad. Okay. So now, so you see that like what we kind of want is like we want that for every node, for most vertices, for most vertex V, we want that V is not ordered too late among its neighbor. Like we want it to be like this, not too late, not too close to delta. Okay. So now we can ask like what ordering can we expect this quite easily? Yeah.
So I think if you, I don't know if this is the right answer, but if you so select V, so let's say you take the top left one, and you kind of like update the graph so that all of the guys on the right now have degree 3. And so you basically take the minimum degree guy.
Mm-hmm.
At least that would work for this graph. I don't know if that works in general, but
that is interesting, and I'm not sure. Yeah, it might I believe that there should be some nice, maybe simple algorithm to give you this ordering. However, we're gonna do something extreme. We're gonna just choose a random order. Why do you think so? Why do you think this should be the case? Because like when you choose random order, right? Okay, if this is the node V, and you have a neighbor, when you do random order, at least you expect like half of its neighbor on before you and half of its neighbor after you. That's what you expect. And this is really good enough for this. You just don't want yourself to be too late in the order compared to your neighbor. And when you do random ordering, you expect yourself to be kind of in the middle. So we just do exactly this. Okay. So let's try to analyze this when now the order is also random. So far we have that like if we fix some order pi, the running time given that the order is pi is just this. We have seen this. But now we're gonna like make some more randomness into the like put more randomness into the algorithm. We use random ordering. So the expected running time now is gonna be like expectation over like over random permutation pi. Give like and then you put the expectation of running time given that the order is pi. Okay. So this is like your expression, the expression of the algorithm, of the runtime. Now my claim is that now it's gonna be not too hard to show this. That 1 over this thing is just gonna be something like log delta over delta. We're gonna see this soon, but once we see this, then it means that the total expected time runtime, well, like each of this term is just log delta over delta. So the total runtime is just n log delta over delta sum over all nodes. So you get this n squared over delta times log delta. Okay, so let's try to prove this. Okay. Okay, so we want to prove this thing. Now, okay, my question is, when you choose a uniformly random ordering pi, okay. First of all, like this thing will range from, it's gonna be at least 0, right? And at most degree of v. Okay. So this is like a number between 0 and degree of v. But what do you think? What is the distribution of this one? When pi is random. There is like a natural guess.
Uniform?
It must be uniform. Why must it be uniform? Because like when you do like a random permutation, there's no bias to any direction, right? So now when you kind of, now it's like you have v and all neighbor of v. Let's say u1, u2, u3, u4. Let's say that v has 4 neighbors. And you do random permutation. But if you just focus on this guy, on these 5 guys, the relative order of these 5 guys will be like will be random permutation too. When you just focus on this guy, it just look like a random permutation of size 5 too. So the position of v relative to all the neighbor is just like a uniform. So the degree here is just like uniformly distributed over this number to this number. Okay. Okay, this is just a uniform distribution. Okay. And once you know the distribution of this one explicitly, you can just like try to calculate this one. Okay. So just from the like this definition of expectation, you know that each of this value occurs with this probability because degree before of v is uniform. And now I claim that like this thing is at most this thing. How to say this? Well, like, what is this expression? This is the average of 1 over I, start from I equals 1 to delta plus 1. But what is this? This is the kind of the average of basically the same object, except that you take like degree v plus 1 smallest elements from this set, and then average. Like you have like this set of numbers, and you take the average, and then now you take like the smallest like prefix, and take the average. So this one must be smaller than this one. And now we're done because what is this? This is harmonic sum, right? Like a sum of 1 over I. So sum of 1 over I is like up to this thing is just gonna be a log of like if it's sum from 1 over I up to 1 over delta plus 1, it's log of 1 over log of delta plus 1. Okay, any question? You all have seen that like you have seen harmonic sum before. Okay, good. So we are done basically. Now we are done. We get this. Question before I go further?
I know you already explained this, but the proof that we just did on the last slide was for looking at one node, correct? So how is it n squared and not n for the next slide?
Oh, yeah, because this is like a 1, I have 1 here, right?
Mm-hmm.
But in the last slide, we have n here.
Okay.
So that's why like you have another factor of n.
Okay. And like, can you just briefly explain again where that, like,
Where did I get?
conceptually, yeah, why there's two n's?
Oh, okay. So okay. Maybe let's go here. This part should make more sense. Yeah. Here.
Oh, right. Okay.
Like the time that we spend on each node. This thing really makes sense because like you either like kind of query all the nodes or you query one color. And this is like kind of the size of the set of one color in expectation because you kind of color each node randomly. So like there are each of the color will have like n over delta in expectation. So you kind of spend this much time on each node in expectation, and there are n nodes.
Okay.
Yeah. And we just say that okay, we don't really spend this time. We spend close to this time on each node.
Okay.
Yeah. Okay. So now that's it. That's like a sublinear time algorithm. Okay. So now I will talk about something new, which is the distributed algorithms, which is another kind of sublinear time. Okay, let me talk about the model. Think of you have computer networks, and like this network, you can model it as a graph, right? Each of the node here is like a computer. Each edge is like some cable connecting them to each other. Okay, and now each vertex can send message to only its neighbor. There's gonna be like a one round. For each round, each node can send only message to only its neighbor. And what we want to compute is something about this network itself, so that we want to minimize the number of rounds. Just think like you have like some network and you want to spread the information throughout the network. But each round you can only talk to your neighbor. Or you want to know where is like a bottleneck of the network, where is the min cut. You might need to know that. Yeah.
Isn't this just very similar to like shortest path in a graph?
Like shortest path is something that you want to compute, but you're gonna see that like we can ask to compute anything in this model. Yeah, it makes sense to ask any question, but yeah, one question that we want to compute, like what we want to ask is like shortest path for sure. Okay, so some toy problems so that you know the model. Like, imagine that each vertex has some number, each node V has a number NV or something. And now you just want to compute the smallest number. Okay, so how many rounds do you need for this graph? Let's say it's a graph of the star. How many rounds do you need to know like a smallest number? Yeah.
Just need one for the top one because because everyone sends their value to the middle guy and then he computes the smallest.
Yeah, everyone just send to this guy, and this guy would know the smallest number. How about cycle when there are like n nodes in the cycle?
N/2.
Yeah, something like n/2, because it could be like everyone here has infinite number, except like the guy on the opposite side, and this guy have, let's say, like some number A, this guy has number B. So like information from these two guys need to like travel through the cycle somehow, and that takes n/2 rounds. Okay. So in general, like for this simple problem, you will need like diameter round, where diameter is like the maximum distance between any two nodes, and diameter can be as big as n. So this simple problem you need a lot of time. Okay. But today we're gonna see we're gonna look at not so simple problem, and you can do it much better than n. Okay, so we're gonna look at maximal independent set. You all have seen independent set many times, right? But we're gonna look at maximal independent set. Okay. So I said that S is a MIS, or maximal independent set, if first of all it's an independent set. There's no H inside S. And another one that I need is that is maximal. What I mean here is that every vertex is either already in S or adjacent to S. And by maximal here, I don't mean maximum. I really mean like, here it just means that like you cannot add one more node into your set so that it remain maximum, so that it remain independent set, because everyone is either in S or adjacent to S already. So for example, this one is a maximum independent set, but this one is also maximal. You cannot add anyone into the set. This one is not MIS because this is like not independent, and this one is independent, but it's not maximal, because you could add this guy or this guy, right? Okay. So now, like, can you imagine some simple greedy algorithm that takes like n rounds on a path, maybe? So like one simple greedy algorithm is like choose any nodes, pick that into your MIS, delete that node and also delete your neighbor, and look at the remaining nodes, pick that node, and repeat and continue.
Is this like not on a distributed graph algorithm? just in general?
This is already like in general. This idea you can implement it in any model, and you can implement it in the distributed model too. That is like just let's say like one node. You start with one node, and this node you pick it into your set, and then it informs the neighbor, and the neighbor will be like kind of removed from the graph. Like will declare that you are done. And the neighbor will now like maybe like inform some of the node, and this node will select itself to the independent set and repeat. Yeah. I'm not specifying the precise way to implement this in the distributed model, but if you are not careful, likely you're gonna pay n rounds. Even if you are careful and you try to use this idea only, you should take n rounds. But you're gonna see like a log n rounds algorithm. So sublinear in number of nodes. And this algorithm is like it's actually like really old. But there is a new analysis that is nice. Okay, the algorithm is here. First, each vertex will sample some number, like some random number in between 0 and 1, call it priority of that node. Okay. And it's gonna send this priority to its neighbor. So now like you know the priority of your neighbor. And every node now know the priority of your neighbor after sending this thing. And now each node will join to the set S if that node V is a local minima. Meaning that the priority of V is like smaller than all of your neighbor or of its neighbor. Okay, so if V is here, and let's say priority is like is 5. Oh no, actually it's 0.1, and all of this is like more than 0.1, like 0.2, 0.3, and something. Then you put V into your set. And you know that if V is a local minima, then none of the neighbor is local minima, because V is smaller than the neighbor. Okay. So you know that like if you put V into the set, then like it's gonna be independent from its neighbor. The neighbor is not included into S for sure. Okay. And once V joins S, it will like this is one round. This is done in one round, and in the next round it's just if we decide like know that V joins S, then we just inform its neighbor that okay, now I know that I'm in S. I tell you, my neighbor, that I'm already in S. So what we should do is now V and its neighbor are now removed. What do you mean by remove? It means that like they will not participate in the future rounds from now. Like think of it like you remove it from the graph. You don't even like the neighbor like what if I receive any message, I ignore it. I don't do anything. Okay. So I think it's now, I hope you are convinced that this algorithm will produce independent set. Because whenever I add V into the set, it's like not adjacent to anyone. And when I remove and when V join the set, in that round it's gonna remove all of its neighbor too. So the neighbor like in future round, the neighbor of V cannot join the independent set ever. So like this guy remain independent. Okay. And once all vertices are removed, then S will be maximal. Well, because like, when do I remove things? Either when I'm in the independent set, when I'm in S, or I'm adjacent to some node in S. If everyone is removed, then like every node is now in the set S or adjacent to S. Okay. So this is the correct algorithm. It returns a correct MIS. We just need to analyze again how many rounds we repeat this loop. And I claim that it's gonna be just log n with high probability. Okay. Any question up to now? Yeah.
This is just kind of the definition of a maximal set. If there's one maximal set with 3 nodes and another maximal set with like 2 nodes, they're both valid, right?
Yeah.
Okay, that's
Right.
yeah.
Yeah. Maximal can have like 2 maximal set can have different
Okay.
size. Yeah. Okay. Good. So now like what do I mean, like why do I choose parity, like a random real number from 0 to 1? I could do it differently, but like the point here is just that when I do it, like when I sample from real number, I just want to simplify things so that like each vertex have unique parity with probability 1. Because if you sample from real number, there's no chance to collide. That's all I want. And once you have unique parity, it just means that it defines an ordering of vertices because no one collide, no parity collide. So from the parity, you can order vertices. Okay, so you get some ordering of vertices again. What would be the ordering? Like what would be the distribution of this ordering? By symmetry, it must be uniformly random because each node just do things uniformly. Everything happens symmetrically. Like there is no bias towards any ordering. So you will get uniformly random order from the parity. Okay. And by the way, if I just want, like, this is all I want, actually. I want like a uniformly random order. Okay. And the reason that I do it like this is just so that I can implement this uniformly random order in a distributed way. I don't need any coordination between nodes, right? Each node just sample some number. If we are not okay with real number, then we could just sample from like a big integer, like big enough integer, like a number from 1 to n to the c, and then you know that like two nodes will not choose the same number with good probability, and if this number is big enough, then like you still have no collision with high probability. Anyway, I would assume from now that ordering of parity is uniform. Okay, uniformly random. Okay, so now how do we analyze this that there are not too many rounds? So what we're gonna do is, let's say that mi is the number of remaining edges after ith repeat loop. Okay. And I claim that on each round, in expectation, the number of edges is kind of half. It just mi in expectation, mi is at most mi minus 1 over 2. And once we have this, we are kind of done easily. because we would not like we can repeat this like so m0 from the beginning is like at most n square. M1 would be in expectation at most n square over 2. M2 would be at most n square over 4 and so on. So m of like log n is something like n square over 2 to the this 2 to the log n. And if you choose c to be big enough, then this is just like n over 1 over n to the c, 1 over n to the c. So in expectation, after log n rounds, you expect something much less than 1. You expect that the number of edges is much less than 1. And now by Markov, right? If expectation is much less than 1, the probability that it's at least 1 is small, just by Markov. So it means that after like something like log n rounds, there's no edge left with high probability, because the probability that there exists some edge left is tiny. So like what I need to show is just this thing basically, that I expect the number of edges to be half in each iteration. Okay. And okay, let's try to prove this. So what we wanted, like, and let me set up some notation. Now let's fix some iteration, right? And from now, let me just use G to denote the graph of this iteration. Okay, it's not like an original graph. G is now the graph, the remaining graph. Okay. And let's say y is the number of edges that I removed. And y of uv is just indicator that an edge uv is removed. So like y is the sum of y uv and overall edges. And our goal is to show that like the expectation of y is at least half of E. Okay. I want to show that I remove in expectation half of number of edges remaining. That's the goal. Okay. And okay, this is a goal. And let's say that I used NU to denote the neighbor set of node U. Okay, and here is an important definition. It said that U firstly Q V. If, let's say that U is here, V is here, if priority of U is before everyone here, basically. If U is before all the neighbor of U and neighbor of V. Okay. So why do I say that it's firstly QV? Because like if U is the priority of U is less than everyone in this set, first of all, it means that like U is a local minima. So U would be included into the set S, right? And then U would like you would be removed after the next in the next iteration together with all of its neighbor, which is V. Okay, but V could be removed by some other nodes too. Like there could be like some other node here. There is a local minima too. Okay, but right now I said that priority of U is less than priority of W. So I kind of say that U kind of kill V first. Make sense? The definition, like the terminology. So like I kind of say that this guy is the guy that like is the key reason that V is skewed because it's like the smallest guy. It's kill V first. With me on the definition? Question?
But W can be the neighbors of either U or V, right?
Yeah, W, that could be like W like this too. Or that can be like W of this, like W here or W here.
So how does it, what's the case when W is just a neighbor of U and not V?
Oh, in this case, W cannot be in the independent set for sure.
Yeah, right, okay.
Yeah. But if W is just neighbor of V only, this guy could be in the set, but like you would kill V first anyway.
Okay.
Yeah. All right.
So that's like a trivial case, basically, like if it's not a neighbor of
Right.
both of them, okay, thank you. Sorry.
So now I just define like I have some indicator that X U to V to send U Q's firstly Q V. That's the indicator. And now observe this. What's the probability that U firstly Q V? For this to happen, I need that probability of U is just smaller than everyone here, than like all neighbor of U and neighbor of V together. But again, we have like a random ordering, right? This is just to ask like among like this set of nodes, union of like neighbor of U and union of neighbor of V, neighbor of U and union and neighbor of V together. They like the ordering of them is uniform. And I just ask like what is the probability that U is smallest among this? But since the ordering is uniform, U would be the first in the set with just like a 1 over the size of the set. That's the probability. This makes sense? This step. Okay. And yeah, and the size of neighbor of U union neighbor of V is just at least this thing. Yeah, at most this thing. So if U and V don't share any neighbor, then like this, if they don't share any neighbor, then this set would have size exactly this. But they could share a neighbor. If they share a neighbor, then the union of this union will have size at most this one. Okay. And now I have some key claim that is not easy to pass. Okay. I'm gonna prove this soon. But let's try to use it. If we have this, then what do we have? Now I can just like analyze expectation of y. Just put expectation on each side, right? So this is like a 2 times expectation of y, and expectation of this whole thing. And by linearity of expectation, we can just put expectation here and here. But expectation of this guy is just at least this. Expectation of this is just a probability that this is 1. So it's at least this one. And so you just see that this thing is at least this one. Okay. And what is this? This whole thing is 1. So you just sum over 1, sum of 1 for e many terms. So this is e. Okay. So assume this key claim, then we are done. Okay. So let's try to prove this. Okay. How do you prove this? We need to like understand more what it means. Like so, okay. So I first of all like I claim the following. I claim the sum of the event that u firstly qv sum over all u, like sum of this indicator that u firstly qv sum over all neighbor of v. This is just going to be at most 1. Because this is an event that u firstly qv, but there can be only first neighbor. Like v is q for first time only once. Right? So if this is v, this is u, if there is like a u prime, if u firstly qv, then like u prime cannot firstly qv. Okay. So like even when you sum over all neighbor of v, like this event are disjoint. The neighbor of v that firstly qv is like a disjoint event. So this is at most 1. Okay. And once v is q'd, then all the incident edges of v is removed. That is, if for some u firstly qv, then you would remove all edges incident to v. That is the sum of whether like you remove the edge uv, they are all 1. So this sum is equal to the degree of v. Every edge incident to v will be removed because v is removed. So just by here, we have this. Right? That is, this sum is at most 1. It can be 0 or 1. If the sum here is 0, then the inequality is trivial. If the sum of xuv is 1, then this thing is going to be at least degree of v. So it's safe for me to multiply by degree of v here. Question about this? You with me? Not really? So it seems I lost people, right? Am I? Okay, I am. Okay. So okay. So I'm just saying that this sum times degree of v is at most this thing. U neighbor of v, u neighbor of v. And why is this? There are just two cases. Either this is 0. If this is 0, nothing to prove.
Yeah.
Another case is that this thing is 1. If this is 1, then I know that this sum is degree.
Oh, okay.
But if this is 1, then this is at least the degree of V. So in these two cases, this inequality is true. Okay. Okay, so once we have this, then I'm just summing this inequality over all nodes, all node B. For the first left-hand side, summing over all V, I just get this one. Because like this is a kind of, when I sum from like for each edge, I have this sum from two sides. Like when I sum from the side of U, I have this term. When I sum from the side of V, I have this term. Like each edge, kind of you did do it from two sides of the two endpoint of the edge. The same for this one. I sum over all nodes here. So each edge will be count twice. Here I just have like a two times this guy, because they are the same from both directions. Here it's just like the same, like not the same from both directions, because U to V and V to U are not the same. So having this two term here, I just get this one. All right. Okay. And with this key claim, then we are basically done. We get that like with high probability, the number of round is just log n. Okay. Questions? Where do I lost you? I'm not sure. You're good or no? All right. Okay. So see you on Tuesday. I'm gonna be here, so ask me anything on that day.